Yeah. Yeah, I'm recording, pa. No issues. We can go with this directly. Have a look. So we have started with units and measurements. A physical quantity is nothing but any quantity which will explain the physical happenings, and it can be formulated as well as which is measured. Most of the sums are based on screw gauge, vernier calipers, time period, errors, and dimension analysis. Now we'll try to go with representation of physical quantity. Okay, how will we represent a physical quantity? So physical quantity is mainly represented with the symbol Q. Q is always written as N times of U. Okay. Can anyone tell me what is Q and what is N and what is U? Usually, just a random guess. Even if it is wrong, no issues. Q is a physical quantity. Here, N refers to a number or a value or a magnitude. Here, U refers to size of the unit. Size of the unit. Fine. So you can always assume that force you are having. Just tell me a random value of force. Anyone? Leave a minute. Okay, some 8 Newton, I'll take it. Now here 8 is nothing but magnitude. It represents N. And N is nothing but size of unit. Okay. Assume you are having the length. Length is a physical quantity. Length I can take it as some 10 centimeter. So 10 is N as well as centimeter is nothing but size, Q value. Even you can convert. Why I am talking about size, I can say it as 10 into 10 power minus 2 meter. Here the size of the unit is increasing as well as the value is changing. So always these units are termed in terms of sizes. These are nothing but the values. A physical quantity will always be associated with a magnitude as well as the size of the unit. Is that clear for everyone?
Yes, sir.
Yes. Okay, let me switch this.
Yes, sir. Hello.
What happened, pa? Okay. But one more thing. So we are having Q equal to N into U, right? So we have one general representation for this. Just a minute. We have one general representation for this. N is proportional to, or I can make it as the physical quantity is fixed quantity. N times of U is always a constant value. Or I can say N is proportional to 1 by U. Have you ever observed this? When will I take N is proportional to 1 by U? Assume you are getting, if value of N increases, U must decrease, no? As I've taken here earlier, I have taken length as some 10 centimeter. Fine. Now, what is the size of unit? Is it a small? Okay, just a minute. Here 10 into 10 power minus 2 meter. Or I can write it as 0.1 meter. Now, from here to here, what happened to the value? N increases or decreases? From centimeter to meter conversion, is N increasing or decreasing? Reply faster. N is? Yes, N is decreasing. As N is decreasing, centimeter is a smaller unit. Meter is a bigger unit. As N is decreasing, unit is increasing. Size of the unit is increasing. Okay. So you can always say whenever magnitude increases, the unit decreases. This will hold true each and every time. That's why I have written as N times of U is always constant. Even you can write it as N1 U1 is always equal to N2 U2. So one unit to other unit, if you are converting, their product will always remain constant. Like that you can mention. Fine. Okay. Shall I switch? We'll just see the quantities. Whatever we are having till now, ratio type we are having, vector type physical quantities we are having, as well as scalar type physical quantities we are having. First, I'll mention the types of physical quantities. Now, PQ I'm mentioning for a physical quantity. Is that okay? Now, ratio type will go first. Then we'll discuss about vector type, as well as we'll discuss about scalar type. Right? Just a minute. Okay, what do we mean by ratio type? Can anyone tell me formula for refractive index? Eta is equal to what? Anyone? Just a formula alone. And relative density. So relative density, I'll just take it as, okay. Deviation, okay. Refractive index will tell you how much, to what extent the speed is increasing and decreasing. I can say eta is nothing but C by V. What is unit of refractive index? No units, right? So this physical quantity is a physical quantity which is ratio type. You can always write it as M0, L0, T bar 0. Physical quantity are you're having numerator and denominator of same type. Even relative density, if you take it, relative density is also in the same manner. It is always some density of water at 4 degrees centigrade are divided by density of substance. Like the density by density, you'll get it. This is also of ratio type, ratio of same type of physical quantities. So you'll always get M0, L0, T power 0 here. Now, can anyone tell me what is a vector type of physical quantity? I'll give you. Force is a vector type of physical quantity, as well as acceleration is a vector type of physical quantity. Okay. Now, talk about scalar physical quantity. Anyone, any scalar physical quantity? Just guess. Give it a random guess. Scalar weight. Okay, mg. Mg is also force. It is vector type. Again, length is vector. Kinetic time. Time we can do. Plus work done we can do. Yeah, I'm getting more answers. Yes. Okay, you can take these 3 types. One type of classification I have done so far. Yeah, speed we can add. Speed is a scalar. Even here I can add velocity. These are the one type of classification. Now weight cannot be a scalar. Weight can be a vector quantity. Mg is acting downward direction. No, you can add it as a vector. Right? Okay, this is one type of classifications I have taken so far. I can take one more type of classification. So based on what others are taking, I can take it as fundamental physical quantity as well as derived physical quantity. So again, one more type of classification, same in physical quantity. First, I'll take it as fundamental physical quantity as well as derived physical quantity. Okay, I think damn me, you guys know this very well. So what are fundamental physical quantities, ma? Okay, how many of them are there? Good, nice. Exactly 7 fundamental physical quantities are there. No, 7 fundamental physical quantities are there. So those are nothing but you can call it as mass. You can call it as some length, time, temperature, intensity. Okay, mass, length, time, temperature, intensity. You can have it as electric current too, as well as amount of substance. So you can take them here: mass, length, time, temperature, intensity, current, amount of substance. Okay, 7 are done. So these are the physical quantities. Now I'll just give you the symbols or units of them. Symbols everyone knows. Units of them. So usually random units I'm taking. MKS I'll take it as of now. So kg, meter you can add. Here you can take it as in terms of second. Here in terms of Kelvin you can have. This is nothing but candela. You can have current, ampere, amount of substance, mole you can write it. So these are the known quantities so far. Yes, 7 exactly. Now, what can you say about derived physical quantity? See, this fundamental quantity is acting like a coach of a cricket team. So a coach will be only one. Okay. Derived physical quantity is like place. Place can be anyone, but the coach is only one. So mass can be written only in terms of mass. Mass we cannot write in other terms. Even length is a fundamental. From the fundamentals only, you can have the derived quantities. Okay. From the coach alone, the players are learning the play. So can anyone tell me some derived physical quantities? Okay, as of now, I'll take it. Force. Force is nothing but, yes, force is nothing but mass times of acceleration. Even I can have acceleration as meter per second square, no? Rate of change of velocity, or rate of change of velocity, na? Velocity by time I can take it. So again, velocity, how can I take it? Change in distance by time into 1 by t. You can always see mass, length, time, everything is a fundamental quantity. So force is a derived quantity which is derived from fundamental quantities. Yes, even you can take power, or even you can take work done. Work is nothing but force into displacement. I can take it. For force, you can write entirely m into L divided by t square into the displacement. Displacement is nothing but length alone again. ml square divided by t square, like that. Clear? Now, derived quantities are many. There is no exact count for it. Actually, there will be a bureau, International Bureau of Weights and Measurements. They are deciding these quantities. If they say this quantity is 1 kg, we are agreeing it as 1 kg. If they say this is 1 centimeter, we are agreeing it as 1 centimeter. Somebody is there to tell us, so this much length is 1 centimeter. This much length is 2 centimeter. And it is accepted universally. As it is accepted everywhere, so we are following that convention. Okay. Shall I switch?
Yes, sir.
So we'll come to the sums part a bit later. So as of now, let us be clear with the basics. Let me have a rough table for it. System of units we'll discuss. As well as here, one more I needed. Okay. Serial number and MKS, CGS, as well as FPS. Along with FPS, we are having standard international. We are talking about system of units. What do I mean by system of units? If you go to America, USA, or if you go to UK, they'll say everything in terms of a pound, isn't it? A pound. They won't say in terms of kilogram. They'll say a pound. They'll say it is 6 feet. Okay. So their usage of units are a bit different. In India, we are strictly following NK system. There, they'll try to follow a different system of units. So that we are going to discuss now. So we'll try to see how different physical quantities are converted in different system of units. So first we'll go with length, mass, as well as, okay, here's instead of serial number, I'll take the physical quantity. Length, mass, and time you can mention. Time is the only quantity which is same in each and every system of units. When you talk about length, how it is represented in MK system? Just tell me the unit. Is it in terms of meter, centimeter, or kilometer, or feet? It is meter, right? In CGS system, it will be centimeter. This first word itself will tell you meter, centimeter, and foot. So you can have it as feet. Feet or foot, your wish. So here, next one is kg. They're talking about mass. This is grams. This is pounds. Pounds is denoted with the symbol LB. LB na libra. Okay. So this is a different system of unit. See, what do you mean by Libra in general? We'll assume that there are 12 bananas. What you call in general at 12 bananas? You'll call it as a dozen. Yes, a dozen. Even in a different country, they have taken some amount of mass. So some amount of mass, they called it as a libra, 1 libra, like that. Instead of calling as a libra, they are taking it as a pound. Fine. So for pound, this one you can take it. Okay. What is SI system? It is just an extension of MK system along with 4 more fundamental physical quantities. 4 more fundamental physical quantities. Fine. So this is just basics we are learning as of now. Fine. Shall I just move further? We'll try to deal with the dimensions. What do you mean by dimension formula? What do you mean by how the derived physical quantities and fundamental quantities are related through the dimensions? Okay. Just a minute. Yeah. First, I'll take dimensions. When we are representing, I'll try to write in rough manner. When we are representing derived quantities, the powers of fundamental quantities, the powers of fundamental physical quantities are raised. So these powers are known as dimensions. These powers are known as dimensions. Clear? See, I'll try to take the formula for force. What is formula for force alone? Mass times of acceleration, no? So how can I take mass? Always remember, for mass, for length, as well as for time, usual representation will be capital M, capital L, and capital T in case of dimensions. So mass here, I'll take it as mass alone as of now. Acceleration, can I take it as, yes, meter per second square will have the formula, no, in general, meter per second square, meter na length, second square na t power minus 2, I can take it. Some length divided by time square. I can write it as M, L, t power minus 2, 1 t power minus 2. This 1 t minus 2 is there, right? These are known as dimensions. Okay. See, you are trying to represent a derived physical quantity. The powers of fundamental physical quantities are raised. So these powers are defined as the dimensions. Clear? Anyone, any doubts? And if you represent this derived physical quantity in a bracket, we'll call it as a dimension formula. This formula you can call it as a dimensional formula. So far you have listened to the lecture. Now it's time for you guys to practice. Okay, let me give you a few questions. So find the dimensional formula for area. Simpler one I'll give you. So for density, for momentum, as well as go for power and pressure. We'll proceed further. Yeah, I got a few answers. Yes. Area na meter square, no? Can I call it as M0 L square t power 0? Yes. Even if you want it, you can write it as L square directly. What about density? Density is nothing but mass divided by volume. So I can write this one as m power 1, L power minus 3 and T power 0. Okay. Let me check. Yes. Risha answered. Itra is correct. Next, momentum. Formula for momentum. Mass times of velocity. Let me check who will answer faster. Momentum dimension formula pa? Itra is correct pa. M, L, T power minus 1 you can have. M power 1, L power 1, T power minus 1. Power. What is the dimension formula for power? Now power you can take it as formula usually. Can I write it as work done by time? How faster or how slower the work is being done? Isn't it? I can write this one as ml square T power minus 2 divided by time is nothing but T. So ml square T power minus 3 I can have. Pressure formula, force by area. Force na, okay, ml inverse T power minus 2 you got. Work done. Okay, I'll try to derive this. Force into distance now. Now for force it is nothing but mass times of acceleration ml T power minus 2 into L. So it will turn out to be ml square T power minus 2. Correct? Check once. Keith Raj. Oh, Kiran Raj. Okay, you have given me for pressure. Pa? Oh, for pressure. Okay, fine. ml square T power. Oh, just a minute. I've taken ml square again. So we can write it as ml T power minus 2 divided by area na L square we can write it. So ml inverse T power minus 2. Easy peasy, right? You no need to struggle further more than this. Yes, ml inverse T power minus 2. But whenever you write it, try to represent them in terms of a bracket. It will become a dimension formula. That's it. Apart from that, nothing new is there, ma. Even we have some formulas based on angular quantities. Okay, dimensions which are based on angular quantities we'll discuss. So we can have angular quantities here. So how the angular quantities will be? Can you tell me one angular quantity? Can I write it as an angular displacement? Angular displacement formula is what, ma? Yes. As well as I can give you angular velocity. Even we can write it as angular acceleration too. So angular displacement is represented with the symbol theta. Now usually theta is nothing but arc by radius. One more example we are having here. Yes, my arc and radius. My arc means some length. Radius also means some length. Which type of physical quantity it is? Yes, which type of physical quantity it is? Length by length. Can I take it as ratio type? And length by length, you'll simply get it as m0 L0 T power 0. Nothing new, we are going to get there. Yes, ratio type. And angular velocity, now omega you can assign over there. Now omega you can write it as d theta by dt, or theta by t, you just take it. For theta, no units. m0 L0 T power 0. For t, you can write it as t. So the dimension formula for omega is nothing but m0 L0 T power minus 1. Clear? Fine. Okay. There will be solid angles and other things too. So when time progresses, we'll just discuss them also here. Those things also will be discussed. Okay. Let me just switch it. Even you can have angular acceleration and other quantities too. Okay. No issues with that. Now we'll try to see. We have discussed about dimension formula and all the things. So what are the applications by seeing these dimensions? What are the, if you analyze the dimensions, so what will happen? How can I implicate in my real life? So there is a branch which will be spoken as dimensional analysis. After analyzing them, so how can we make use of them? So from now onwards, the real physics starts, you can say. Okay. So what is the first major application from dimension analysis? First application is nothing but when you want to convert one system to another system. Okay, when one system to another system, conversion is happening. So you can very well use this dimension analysis as well as to check the consistency of equation. Yeah, used to check if the equations are correct. Good. The consistency of an equation will be checked, as well as if you know dependency between, assume that the force depends on I can say it as mass, as well as it is proportional to some v square, as well as it is inversely proportional to r. So derive the formula for centripetal force. They will say centripetal force is nothing but mv square divided by r. Directly we can have, if you know the dependency on what factors the centripetal force is depending, so we can deduce a formula for it. You can write here to deduce the relations between physical quantities. Okay, so we'll try to discuss each and every one of them one by one in an order. Okay, fine. Okay, how we can deduce the relation between each and every physical quantity, and how we'll check the consistency, and one more thing. Okay, dependency. Fine, fine. Consistency, dependency, and dimension analysis. Okay, just a minute. So supplementary angles also we have taken, as well as dimensions of physical quantities also we have taken. Okay. First we have checked the consistency. Later we can convert. Yeah, conversion we can take in this manner. Now, what is the relation between n as well as u? Relation between n and u, whether they are directly proportional or inversely proportional, or they are equal. Yes, they are inversely proportional. So you can take it as n is proportional to 1 by u, or you can make one more note. N1 u1 is always be equal to n2 u2. Okay, we are using this fact of a physical quantity, and we are trying to convert one system of units into other system of units. Even if we are having any unknown equation, yes, even if we are having any unknown equation, based on this one, we can try to convert one. Right? So I'll try to tell you with an example. So how can we convert one system of units into other system of units? So 99% of the cases, this example will be taken. So try to convert 1 Newton in terms of dyne. Okay, or 1 Newton in terms of different system of quantities. Fine. Shall we go with the work done? Try to convert joules into ergs. What is n? But n is nothing but magnitude. Magnitude or value. So we'll take it at 10 newtons. No, 10 is the n. Newtons is nothing but size of the unit. Fine. U is nothing but unit. Fine. Okay, we'll try to convert